Talk about regression analysis. This is building on our concepts that we learned when talking about correlation. All right, there's three broad categories of regression analysis. There's simple linear regression, multiple linear regression, and logistic regression. Simple linear regression uses one independent variable to predict a dependent variable. Multiple linear regression is used to examine the effects of two or more predictors or independent variables on an outcome measure or dependent variable. And these are on continuous scales. Logistic regression uses two or more predictors to predict a binary outcome. Like, for example, did they vomit, yes or no? And that would be considered a dependent variable. With multiple linear regression, this also allows us to include categorical or dichotomous variables that we can control for, or we can analyze the effects of on the dependent variable under study. All right. Linear regression, it assists in making predictions about how change in one variable affects another. For example, we're looking at how patient age, does patient age predict the inhalation anesthetic requirements, or the MAC. The dependent variable is on the y-axis here. The independent variables are on the x-axis. Those are also what's considered manipulated, or the predictors. And what it does with the analysis is it calculates a line of best fit, or a regression line, using this method of least squares to describe, interpret, and predict the relationship between these two variables measured on a continuous scale. It also includes a random error term to account for inaccuracies in the predictions, and it can quantify those accuracies within your 95% confidence interval. So a common regression equation formula would be a y, which is your dependent variable, and then you have what's called the intercept, which might be the beta 0, and then you have a slope, which is how the change in one variable is predicted by another, usually the beta 1, and that would be your independent variable, so your slope times the independent variable value, plus this random error term. So here's a regression line. Again, if we look at that, so we have our intercept on the y-axis, which here is represented by the beta 0, and the beta 1 times the value of the x, the independent variable, plus a degree of error. So that's degree of error between what they might refer to as the residuals of what is predicted and what is actually observed. So say, for example, you can see this in the statistical model here. Y would be considered the random response of ith case. Beta, the slope and the intercept terms are also what's referred to as parameters. You're going to see that, you're going to hear that term a lot. And then xi or x1 here is the known constant. This is the value of the predictor variable for that particular case. And E is that random error term. And you can see a lot of fancy algebra there that you don't need to understand the nuances of. Just know that that's how you sort of are looking at it. The last point that it talks about is that random errors are independent, meaning they're uncorrelated with, and so that's one of those things. Is multicollinearity is an assumption we'll talk about. You have to watch for with regression. And so the beta 0, or the intercept, represents the mean response when the x value is 0, and is referred to as the y-intercept right here. Also, the beta 1 represents the change in the mean response as x increases by 1 unit, and that's called the slope. So with regression analysis, when you're using multiple independent variables, the coefficient can tell you how much the dependent variable is expected to increase or decrease when the independent variable increases by 1, while you're holding constant or controlling for or adjusting for the effects of the other independent variables or predictors within that model. What we're trying to do is model this straight line from our data set. You also have to keep in mind of what unit of measure you are using. So let's look at an example. A study is conducted to determine if pain scores are predictive of morphine consumption. The beta 1 is the regression coefficient, or this particular parameter estimate. The pain score came up with an beta coefficient or beta regression of 5. So this tells us for every 1 unit increase in pain scores, that morphine consumption increases by 5 milligrams. So if it was 2 on the pain score, a 2-point increase, then that would be 10 milligrams. Now, we have to throw in so that you are at least familiar with some of the different tests that they use, and the distributions of the data help define what type of test you use. So an F-test is what's used in a regression analysis, and it uses an F distribution, which you can see here. And it's non-symmetrical. And it tells you if the means between the two populations are significantly different. If it is significantly different, then we disprove our null hypothesis, or we reject it. And the F-critical changes are based on, it's determined based on the sample size and also what's called the degrees of freedom. And these are the number of values in the final calculation that can vary. All right, so let's go through an example of a simple linear regression. This is from our example that we talked about earlier. Can we predict morphine consumption from pain scores? Our null hypothesis, or the H under little score 0, no linear relationship, meaning our probability is greater than our alpha of 0.05. An alternative hypothesis, or the one that we're predicting, is that there is a linear relationship, and we will accept that if our p-value, our probability, is less than 0.05. So what we did, I ran this through GraphPad. I ran some statistics. So our y-intercept was 4.6. Our slope was 1.6, or that was our regression coefficient. So if we were to put that into a regression to try and predict, we would have 4.6 plus 1.6 times the pain score would equal how much morphine was consumed. This is the result of that statistical test. The F was F value was 341, and these are your degrees of freedom. And it was significant, so we rejected the null hypothesis. And the model of fit, the fit of the model was good. And this is where we can also look at the R squared, and we'll talk about that in a moment. Let's just suffice it to say that an R squared of greater than 50% is adequate, and greater than 70% is good for model fit, meaning we're fitting that line. We did a good job. And this just shows you some example of that data. So here, our slope was 1.6, and it gave us a standard deviation there. We also got our 95% confidence interval of 1.4 to 1.8, so that's very tight data, very precise. The R squared shows up here, and you can see the statistical result in the equation right here. So with multiple regression, now we're building on linear regression. We're just adding more variables into the mix to help do a better job of predicting a dependent variable, or that outcome, that continuous outcome that we're interested in. So that's what's represented over here, where now we're just adding in additional parameters we're trying to estimate. So B2, B3, and so on. Plus we still have that error term of random error that's built in there, okay? Or what they may refer to as the regression residual, or the error term. Y is our dependent variable. The X's are the number of predictors or independent variables. A is that intercept on the y-axis when X is 0. So, for example, this is where you can include some nice thing with multiple regression is you can include categorical variables into the mix as predictors. And so maybe we want to see if there's differences in pain scores by anesthesia type, or by gender, or by race. And there's a number of different techniques that we use for entering our predictors into our model. So that basically what you do is you're clicking on them, and you can tell it how it wants to put in those variables in this bucket. And depending on how you do that can affect the results. And it's a whole other, and that's a little bit more advanced discussion in statistics. But suffice it to say, the most common type that people use is stepwise regression or stepwise selection of variables. When there's actually a button that you can select in the program that will, in the software that does that. Because and you can use that because it helps weigh the impact of independent variables separately and in combination. The one thing you have to be worried about is entering too many predictors into a model. And the rule of thumb is for every one predictor, you should have 10 observations.